Today in this session we shall discuss Zeeman effect. What does it mean? It was first discovered by Zeeman that a spectral line placed in a magnetic field and observed through a spectroscope of high resolving power is seen to be split up into several components. When the applied field is high, the splitting is comparatively simple and is known as normal Zeeman effect. When the applied field is less intense, the splitting is more complex and is known as anomalous Zeeman effect. Now, what is the reason behind it? Why a spectral line gets resolved into several components in presence of a magnetic field? An electron, if we consider it is rotating in an elliptic orbit and it has orbital motion, then the magnetic moment related to its orbital motion, which is represented by mu L vector, it is LEH by 4 pi m. It was discussed in our previous session. As a magnetic field is applied, obviously the motion will be affected and the change in its state from initial to final will give rise to the change in the potential energy for that charge. Here is the diagram, and along the z direction, if we apply the magnetic field B, and here is the L vector, and following the space quantization rule, if it is that theta, follow my cursor, through which that orientation is under permission, then the change in energy from its initial to final as the L vector changes due to the application of the magnetic field B, that change is related to the expression mu L dot B. It is a well known expression. That is, when we have the product of the magnetic moment and the field intensity, then we get the related change in its potential energy. That is the change in energy. And if we have the mod, then just having the dot product in its valued form, then mu will be cos theta, where theta is the angle between L and B vector. So, arranging this term, we get, just putting the value of mu L, we get EH by 4 pi m into B into L cos theta. And previous discussion we have learned L cos theta is nothing but ml, magnetic orbital quantum number, and mu B, it is called Bohr magneton, it is EH by 4 pi m. So, ultimately the expression turns to be delta E mu B into B into ml. If EI and EF are the energy states of the electron following its initial and final condition after the application of the B, then we can write the change in the two states, the energy states, that is EF minus EI, the summation of the two parts. One is the change of the energy before the application of the magnetic field, and the rest part is the change in energy due to the application of the magnetic field, where EI naught and EF naught are the energy states of the electrons in its initial and final condition in absence of the magnetic field, and the rest part is due to the change of presence of the magnetic field. and it is the total condition EF minus EI. And delta ml is the change in magnetic orbital quantum numbers related to the initial and final state of electron orbital angular momentum. So we can express, that is EF minus EI, if it is h nu, then EF naught minus EI naught is h nu naught, where nu is the frequency of radiation emitted by the electron for its transition from EI to EF, and nu naught the change in frequency in absence of the magnetic field. So finally, from this expression we can arrange the terms nu equal to nu naught plus EB by 4 pi m into delta ml. From that we can get the three frequency conditions. If we put delta ml 0 and plus minus 1, and this condition is arising from the selection rule, and remember, selection rule is totally the experimental outcome. From the experimental data, when we will try to match some theoretical point of view, that theoretical product, then we should match the both. So the experimental outcomes gives that delta ml should be 0 or plus minus 1, otherwise we shall not be able to develop this theoretical background. So under this selection rule, the three frequencies are nu 1, nu 2 and nu 3. Putting delta ml 0, it is nu naught, that is the unchanged frequency. Putting delta ml plus 1, this is the changed value when it is added, and that is the changed value when it gets subtracted. So a radiation having frequency of radiation nu naught will be seen as three spectral lines. And note, as it is the frequency equation, so EB by 4 pi m has the unit of Hertz, and name of this term is known as Larmor's frequency or Larmor's precessional frequency. Later on we shall try to discuss in detail what is the meaning of the Larmor's frequency. So explanation of the splittings of D1 and D2. We know the meaning of the D1, also the D2. How does it changed? Let us see. So it is the example of the normal Zeeman effect. How does it change? So D1 transition takes place from 3 to S up to 3 to P up, as we have checked earlier. L equal to 0 for S state, L equal to 1 for P state. So that is the transition diagram. Follow the cursor. So here is the absence of the magnetic field, that is the one line is there. 3 to P hub to 3 to S hub, one line, single line. But when there is a magnetic field, that L value gets changed to its ML value, that is plus 1, 0, minus 1, and here as L equal to 0, ML value is only 0. It is the ML value column. So the transition will take place following the selection rule. Plus 1 to 0 means change is plus 1, 0 to 0 means change is 0, minus 1 to 0 means change is minus 1, that is delta ml plus 1, delta ml 0, delta ml minus 1. Follow the diagram carefully. So here the single line gets transformed under the transition in three lines, where the middle one is the unchanged or the initial one, because nu equal to nu naught, as we have seen earlier. So after checking the D1, we can again check the D2 in the same way. Only the J factor changes in case of the D2, and the transition is looking like that. Here note, there is no change in the other formation here, because we have not considered the J value, J factor here. We have only considered the L factor for this type of phenomenon, that it is under normal Zeeman effect. So here is also the 3 to P 3 by 2 and 3 to S half, this transition, it is showing a single line under magnetic field, just from the, as we follow the previous, in case of the D1 the same thing is happening, the 3 lines, again it is originated following the selection rule. So ultimately, if we compare the two transitions side by side, the pattern are same, because the L value and the S value are same for the both, because we are not considering the J factor. Only here the change in the J factors are there, but no change in the L or S factors. So the transition is almost looking like the same. ML values are same, everything are same. The initial one the single line, finally we have got 3 lines. So a single line is seen as triplet under the application of the magnetic field, and we get the 3 lines with nu naught equal to C by lambda naught for D1. D1 value is 5896 angstrom or 589.6 nanometer. In the similar way, we get the D2 lines having the 3 lines in presence of the magnetic field. So what is the meaning of the Zeeman shift? Zeeman shift is the meaning of the, what is the change in wavelength. We can notice the change in frequency, that is the, from this equation nu equal to nu naught plus minus EB by 4 pi m. Why plus minus? Because delta ml either plus 1 or minus 1. When it is equal to 0, then nu equal to nu naught. So nu naught plus minus delta nu, we can get the change in frequency. What is the change in wavelength? That is the d lambda. The meaning of the d lambda is the Zeeman shift. And if we put nu equal to C by lambda after differentiation, we get d nu equal to minus C d lambda by lambda square. That is d lambda equal to minus lambda square by C d nu, and ultimately the Zeeman shift gives d lambda, that is the delta lambda, equal to plus minus lambda square by C EB by 4 pi m. It is very important relation, try to remember it. So ultimately what we get here, the normal Zeeman splitting of a spectral line, if we consider the another transition like L equal to 2 to L equal to 1, previously we have seen D1 and D2, that is L equal to 0 and L equal to 1, in between the two states when the magnetic field arises, then what is the change? If we consider another example, so where the transition takes place anywhere somewhere like that, in between L equal to 2 to L equal to 1, how the transition looks like? It is the transition. So L equal to 2 to L equal to 1, again the single change, and remember the selection rule tells delta L equal to 0 or plus minus 1. So here is the change is single line following the selection rule, and if we get the column of ML values as L equal to 2, so ML values will be different, 5 different values following 12 plus 1, that strategy, that is plus 2 plus 1 0 minus 1 minus 2. Here is also under L equal to 1, ML values are the 3 values, plus 1 0 minus 1. So ultimately just consider the change where this transition occurs. Under the 3 conditions where the delta ml plus 1, under the 3 conditions when the delta ml 0, and under the 3 conditions where delta ml minus 1, we get this transition diagram. But remember, here the number of lines originating, it is not 9 lines. Just follow the explanation. That is, when delta ml plus 1 can occur and when it can occur in the three ways. Similarly, in other cases when the delta ml 0 or delta ml minus 1, these conditions, the three conditions can occur in three ways in the previous diagram. These three possibilities for each delta ml value gives birth of one spectral line. So, if we just go back to the previous diagram, just see the delta ml plus 1, it is actually occurring in three ways. Follow the cursor. When plus 2 to plus 1, change in delta ml plus 1. When plus 1 to 0, again delta ml plus 1. When 0 to minus 1, again delta ml plus 1. It does not mean that the delta ml values are different. As the delta ml equal to plus 1, so nu equal to nu 0 plus EB by 4 pi m. So, it is the way through which it can be changed, the number of ways. So, as nu equal to nu 0 plus delta ml EB by 4 pi m equation only depends on value of delta ml, not on its conditions. Those are to be taken place. So, one spectral line generated for L equal to 2 to L equal to 1, change in energy state gives birth of three spectral lines. Remember, not 9 lines. So, again if we go back to the previous diagram, the single line gives the birth of three lines in the presence of magnetic field. But here we remember, we are considering only the change in L value. We have not considered the change in J value. When we will consider the change in J value means the joint venture of L and S. When we will couple the orbital quantum number and the spin quantum number, then the features will be different, and it goes to the formation of another number of lines, and it is the phenomenon known as anomalous Zeeman effect. Next session we shall discuss about it. After this, goodbye.